Hello everyone, Ross Satchell from Microchip Technology again. Today we're taking another look at the Zero Cross Detect or ZCD peripheral. So let's quickly go over what was covered in the previous video. In the last ZCD video, link in the description below, we went over what a ZCD is, how they traditionally worked, the problems with the traditional implementation with regards to modern process technologies, the on-chip ZCD peripheral implementation, how the peripheral implementation works, and why this implementation is a much better solution. This time we will go over setting up a ZCD in Atmel Studio using the Atmel START extension. Before we go over setting one up, a brief refresher of what a Zero Cross Detect or ZCD peripheral does. ZCDs are used to detect when an AC signal, which is often mains voltage, crosses the 0 volt threshold. It can be used as a frequency counter, accurate long-term time measurement, or for dimming or switching in power electronic circuits. It also finds applications in detecting the presence of mains voltages as part of low-cost safety switches. The zero cross threshold isn't at 0 volts, it's actually at about 0.8 volts. This is because it would make the ZCD peripheral much more expensive and have much higher power consumption to have a ZCD that detects at exactly 0 volts. As a result, 0.8 volts is about as low as the process technology allows without introducing charge pumps, which are expensive and consume far more current. Since the input voltage is likely to be mains power ranging from 110 to 240 volts, that 0.8 volt zero crossing point is negligible for most applications. So now that we've covered that, let's set up the ZCD in Atmel Studio using the Atmel START extension. If you don't have the START extension installed, go to Tools, Extensions and Updates, Atmel START to install it. Since playing with mains voltages can be dangerous and therefore many people may not be comfortable with that, we will use the digital to analog converter, or DAC, on the Avr DA to create an output sine wave with a peak-to-peak amplitude of about 2 volts. The DAC on the Avr DA has a 10-bit resolution and an output buffer, so it should be more than sufficient to create a nice sine wave. So let's get started. If this is your first time using the DA family of devices in Atmel Studio, you will need the device pack. Go to Tools, Device Pack Manager to open it. If you can't see the Device Pack Manager in the Tools menu, then try running Atmel Studio with administrative privileges. In the Device Pack Manager, scroll down until you see Avr-DX_DFP and install the most recent version. Now that's done, we're going to use the START extension to open an example project, then modify it for our purposes. Connect your Avr DA Curiosity Nano board to your computer and you should see the kit window with a picture of the Avr 128 DA48 Curiosity Nano. On that page there are several links for creating new and example projects using this board, as well as the Curiosity Nano schematics and kit homepage. To use the START extension within Atmel Studio, click File, New, Atmel START Example Project, which will open a window inside Atmel Studio. On the right side you will see a drop-down box labelled Board. Click it and select Avr 128 DA48 Curiosity Nano from the list, and you will see a list of examples for the Avr DA. Scroll down until you see LED blink with timer interrupt Avr DA. Click to highlight it, and then click Open Selected Example. You should now see the START example loaded. So before we start adding things, let's quickly go over what we want to do. We want to use a digital to analog converter, or DAC, peripheral to create a sine wave with an amplitude of about 2 volts peak to peak. To do that, we will use the timer interrupt example to load a new value from a sine wave lookup table into the DAC. We will also need to set up a voltage reference to set the DAC sine wave amplitude. Finally, we need a ZCD peripheral to detect when the zero cross occurs and to produce a square wave output. Click on Add Software Component, and then the plus sign next to Drivers, and then add DAC, VREF, and ZCD peripherals. You can see the selected components down the bottom now. Click Add Components, and you will return to the example start screen with the peripherals now added. So let's set them up. To ensure there's minimal latency in our interrupts, we want to run the Avr DA reasonably fast, let's say 16 MHz. To do that, click on the Clock Control button, click on the Clock Selection drop-down box, and select Internal High Frequency Oscillator. Then in the Frequency drop-down box, select 16. Then for the Timer 0 peripheral, if we use a prescaler of 8, that gives the Timer 0 peripheral a 2 MHz clock signal, which has a period of 0.5 microseconds. We're going to set up the Timer 0 peripheral, but before we do, we need to think about it in relation to the sine wave lookup table that we will be using. But first, what is a lookup table? Well, a lookup table is just an initialized array that contains pre-calculated information. They are most often used when we want to avoid complex calculations, as they tend to use a lot of processor cycles. To create the sine wave lookup table, I just googled sine wave lookup table generator and clicked on the first result. The one I used had 3 fields for the user to fill in: number of points, max amplitude, and numbers per row. The first 2 are related to the generated sine wave itself. The last one is how the generated numbers are presented. You could put all the numbers on one row, or you could break it up a bit, say 10 numbers per row, to make it easier for a human to read. The Avr DA has a 10-bit DAC, so I'm going to use the full resolution and select the max amplitude to be 1023. I'm going to use 256 points in the table, but this is arbitrary. You could choose pretty much anything here. For the last field, I selected 10 for the numbers per row. Then generate the table and copy the output. Now that we've got the lookup table sorted out, let's figure out the Timer 0 peripheral. So we've got a peripheral clock signal of 2 MHz, which, as I mentioned before, has a period of 0.5 microseconds. We want to emulate a 60 Hz main signal, which has a period of 16.7 milliseconds. Since we're using 256 values in the sine table, we can work out the value we need to use in the Timer 0 period register as follows. If we divide 16.7 milliseconds by 256, the number of values in the table, that gives us 65 microseconds for each value in the lookup table. Then if we divide 65 microseconds by the peripheral timer period, which is 0.5 microseconds, that gives us 130. This is the value that we need for the period register in Timer 0. Note that Atmel Start auto-detects what type of value we are entering, whether it be decimal, hex, octal, or binary. That's it for the Timer 0 peripheral. Now let's set up the DAC 0 peripheral. All we need to do here is enable the DAC, enable the output buffer, and select the output pin. There's only one option for the output pin, which is pin PD6. That's it for the DAC 0 peripheral. Now let's set up the VREF 0 peripheral. We just need to enable the reference to be always on for the DAC and to select the reference voltage. At the start of this video, I said we wanted to use a 2-volt peak-to-peak signal. In the reference voltage selection drop-down box, we can see there is a 2.048 volt reference available, which is good enough for what we're doing here. So select that one. That's it for the VREF 0 peripheral. Now let's set up the ZCD 0 peripheral. All we have to do here is enable the ZCD, enable the output on the ZCD, then set the input and output pins. I am setting the input to pin PD1 and the output to pin PA7. That's all of our peripherals set up. Now we can click on Generate Project at the bottom of the page. That will then generate all of the code for the peripherals we just set up and present a pop-up where we can name our project and decide where to put it. Once we've done that, it will set up the file structure for us and we can go through and open the files we need to edit. In this case, we want to edit the driver isr.c file, as the sine wave will be created using interrupts. So locate that file in the Solution Explorer and double-click to open it for editing. In the driver isr.c file, just after the include statements, we can declare and initialize an array of type uint16 named sine table with 256 elements. Then paste the generated lookup table that we copied earlier. The one I used had an extra value. It had 257 values rather than the requested 256, and an extra comma at the end, so I had to delete those. And don't forget the semicolon at the end. Next, we need to declare a variable called counter and initialize it to 0. Since we are using 256 values in our lookup table, I'm going to make the counter variable an unsigned 8-bit integer variable. Now we can do our interrupt handling code. So let's first go over what we want to do. We want to write to the DAC an element in the lookup table that's indicated by the counter variable. Then we want to increment the counter for the next time the ISR is called. Since the counter variable is an 8-bit unsigned integer, after it reaches 255, it will roll back over to 0 again, so we won't need to reset it. To do the first one, we can just type DAC_0 and then hit Control Space, which shows us the functions we can use. Select DAC0 set output from the drop-down list. Now we want to pass it the lookup table, which I've named sine table, and the element of sine table that counter is up to. Next, we want to increment counter. As mentioned before, we don't need to reset counter. However, if you used a smaller lookup table, then you would have to reset counter once it reaches the size of sine table. Now build a project to check for any errors, and we can see the build succeeded message. Now we can click the Start Without Debugging button to program the device and run the code. Now for the hardware setup. We need to connect the output of the DAC to the input of the ZCD. However, we need to add a current limiting resistor to protect the ZCD peripheral. If we take a look at the Zero Cross Detection Module Technical Brief, TB3138, link in the description below, on page 2 it gives us the equation for calculating the value of the current limiting resistor. Now normally the input signal would be a main signal that oscillates around ground, so for that case V peak would be half of the peak-to-peak signal. However, since for this demo application we're creating a sine wave that ranges from 0, or ground, to 2.048 volts, we need to calculate our current limiting resistor with that in mind. So for the demo signal coming from that DAC, our V peak is 2.048 volts. Then using the equation, we get the value for R1 as 6.8 k ohms. I have on hand a 6.8 k ohm resistor, which I will place between the DAC output on pin PD6 and the ZCD input on pin PD1. Now let's take a look at the oscilloscope. I have channel 1 in yellow and channel 2 in blue. Channel 1 shows the sine wave generated by the DAC. You may notice that the sine wave appears to have been rectified, that is, its negative half has been removed. This is due to the ESD protection diodes on the input pin of the Avr DA. If I disconnect the DAC output from the ZCD input, we can now see the full sine wave generated. Reconnecting the DAC output to the ZCD input via the current limiting resistor, we can see as the sine wave crosses the zero crossing point of about 0.8 volts that the ZCD toggles, creating a square wave output with a period equal to the period of the input sine wave. So this demo shows just how easy it is to use both the 10-bit DAC peripheral and the ZCD peripheral on the Avr DA family of devices, making your next project a breeze. Don't forget to smash that subscribe button, as well as click the notification bell to ensure you don't miss any new Microchip content. Thanks for watching.